Now that we've built a solid foundation in object-oriented programming with a deep understanding of inheritance, polymorphism, and method and operator overloading, we're ready to tackle one of the most powerful and elegant features in C#, the interface. In the real world, a class might need to behave like multiple types. While C# avoids the pitfalls of multiple inheritance, it provides a smarter alternative, interfaces, to help us build extensible, flexible, and polymorphic systems. So in this lecture, we'll explore what interfaces are, how they solve common design challenges, and how to implement and use them effectively in your programs. This is Lecture 6 of our Object-Oriented Programming course. Today, we focus on interfaces in C#, their structure, use cases, and role in professional software design. By the end, you'll not only be able to write interfaces, but use them to produce better, more scalable code. Here's our roadmap. We'll start by understanding the problem of multiple inheritance, then introduce interfaces as the C# solution. We'll examine syntax, implementation techniques, best practices, and see how interfaces enable true polymorphism across unrelated classes. Later, we'll cover modern C# features like default interface methods and wrap up with a comparison to abstract classes. Multiple inheritance allows a class to inherit from more than one parent class, but it comes with major headaches. The classic diamond problem arises when two parent classes inherit from the same base. Which method version should the subclass use? C# avoids this entirely by not allowing multiple class inheritance. This simplifies method resolution and improves code clarity. Instead of allowing multiple class inheritance, C# uses interfaces, contracts that define what a class must do but not how. Interfaces contain only method and property signatures, no implementation. This means different classes can implement the same interface in their own way, enabling polymorphism without ambiguity. Naming conventions help too. Interfaces usually start with an I, like IComparable or IDisposable. In this example, we show how a class can inherit from one base class and implement multiple interfaces. The student class inherits from person and implements IComparable and IDisposable. The rule in C#, a class can inherit from only one class but any number of interfaces. Also, every interface member must be implemented. Otherwise, you'll get a compiler error. Think of interfaces as plug-in points for capabilities like sorting, cleaning up resources, etc. Let's look at some built-in interfaces in the .NET framework. IComparable lets you define custom sorting logic. IEnumerable allows a class to be looped over using forage. IDisposable is for resource cleanup, great for files, streams, or database connections. Equatable provides custom equality comparison, especially useful for value types. These are great examples of how interfaces enhance flexibility and functionality. Why use interfaces? First, loose coupling. Your code depends on what something can do, not on what it is. Second, testability. Interfaces make it easier to write mock objects for unit testing. Third, polymorphism. You can pass around objects of different types as long as they share the same interface. Finally, extensibility. Want to add a new payment method? Just implement IPayable in your new class. Some practical advice. Follow the single responsibility principle. One interface equal one job. Apply the interface segregation principle. Avoid fat interfaces. Instead, define small, specific ones. This leads to cleaner, more maintainable code and lets classes implement only the interfaces they truly need. Now let's implement a simple IPayable interface. It has two members, calculate pay and get payment summary. Here, the employee class implements this interface. The pay is calculated from hourly rate times hours worked. The summary is formatted nicely using C for currency. This shows how business logic can be encapsulated cleanly in interface implementations. Now another class, invoice, also implements IPayable. Notice it has no hours or rate, it just returns a flat amount. This is where interfaces shine. Employee and invoice are very different classes, but because both implement IPayable, we can treat them the same way when calculating payments or generating summaries. That's polymorphism through interfaces. Let's recap. C# avoids the complexity of multiple inheritance by using interfaces. A class can inherit from one class, but implement many interfaces. Interfaces define a contract with no implementation pre-C# 8.0. This enables flexible design, better modularity, and true runtime polymorphism. We saw this in action with iPayable and our student example implementing multiple interfaces. At its core, an interface is a contract. It says, if you implement me, you must implement these members. It ensures consistency. For instance, every class that implements iDisplayable must have getDisplayText and display. Interfaces cannot be instantiated and don't hold data, just method and property signatures. This slide shows the syntax of defining an interface. Use the interface keyword. No access modifiers on members. They're always public and abstract. Interfaces can contain methods, properties, indexers, and events. The naming convention is to prefix with I, like iPrinter, iSavable, iDrawable, etc. Here's a practical example. iDelete interface with one method, delete, two classes, textbox and car, implemented. Each class provides its own logic for deletion. This is powerful because now we can treat both objects through a common interface and invoke delete, even if we don't know the exact type. This example extends the previous one. We create textbox and car, but invoke delete via an iDelete reference. This demonstrates runtime polymorphism. The correct delete method is called based on the object's actual type, not the reference type. Interfaces can contain abstract methods, properties, getSet, indexers, events. All members are implicitly public and abstract, no need to declare it. Interfaces can also inherit other interfaces, enabling specialization and reusability. Here we discuss two ways to implement interfaces. Implicit, methods directly match the interface and are publicly accessible. Explicit, method is tied to the interface and must be accessed via the interface type. Use explicit implementation when you want to hide a method from regular class use. Great for resolving naming conflicts. In this example, the product class implements iDisplayable implicitly. Both getDisplayText and display are implemented as public methods. This means you can access them directly from the objects. Here, the customer class implements iDisplayable explicitly. The methods don't appear in the class's public API. You can only access them through an iDisplayable reference. This is ideal when you want to implement multiple interfaces that might have conflicting method names. This is a practical demo of using interfaces in a list. We create a list of iDisplayable items, a product and a customer. We loop through the list and call display on each. Even though the classes are unrelated, the shared interface allows us to treat them uniformly. This is a textbook case of polymorphism via interface types. We've just completed our introduction to interfaces in C#. We've seen how interfaces enable flexible, decoupled design, provide runtime polymorphism, and promote clean, testable code. Through examples like iPayable and iDisplayable, you now understand how unrelated classes can share behaviors and how to implement and invoke interface methods both implicitly and explicitly. Now that the fundamentals are clear, let's transition to more advanced interface features, interface inheritance, default implementations introduced in C# 8.0, and compare interfaces with abstract classes. These insights will sharpen your architectural thinking and prepare you to build professional-level systems.